This video in the lecture on cell balancing discusses active balancing. It's a short one. Passive balancing is the most common approach to balancing, drawing energy from the highest cells through a passive element, namely a resistor. The energy difference is dissipated as heat. This is a lossy method. It's also the industry standard approach. Active balancing refers to using some circuit to shuttle charge between cells. The energy is not lost. It's moved from one cell or group of cells to another cell or group of cells. Sounds great, right? It turns out active balancing rarely makes sense. Remember how we looked at relative magnitudes of system currents and found that imbalance is relatively small? The value of the energy burned with passive balancing turns out to be small relative to the cost of implementing an active balancing circuit. Let's take a closer look anyway. For simplicity, consider a 4-cell battery pack. We need some way to move charge from any arbitrary cell to any other arbitrary cell. One possibility is switches. Maybe we could just connect the high cell to the low cell and let them equalize by putting them in parallel. Maybe we include some low-value resistors to limit the current. That's conceptually simple. Let's count how many switches we need. If we have n cells, we need n-1 high current switches. By high current, I mean high enough to carry the maximum application current. So if this is a 200 amp-hour battery that may be discharged at 1C, like a home energy storage battery, we need switches that can conduct 200 amps. We also need 2N low current switches. These don't need to conduct the application current. They only conduct the balancing current. Note that this circuit lets us balance one pair of cells at a time. To balance more than one pair of cells concurrently, we would need duplicate copies of the low current switch and resistor network. Also, this topology can only run balancing when the application is offline, since the high current switches interrupt the normal application's current flow. Consider finding some appropriately rated switches and estimating the cost of this solution for a stationary energy storage battery with 12 to 14 series cells, or an automotive battery with 100 series cells. More frequently, I've seen proposals for active balancing using either capacitors or inductors as storage elements. This allows us to omit the high current switches, which substantially reduces the implementation cost. The implementation shown here would switch the purple cell to charge a capacitor or inductor, then open the purple switches, then close the orange switches to discharge the stored energy into the orange low cell. With a capacitor as shown, the switching frequency allows control of the current, just as in a switched capacitor circuit. Here are some further resources if you're interested in learning more about active balancing. I know I sounded a little negative about active balancing. I'm always interested to learn though. If you work on a product in which active balancing makes sense, let me know. I'd love to learn and to improve my slides. I have one last slide on active balancing circuits. Let's think about how to control all those switches. Notice that these switches operate at different voltages. If we implement the switches as relays, the situation is conceptually simple since the control voltage is independent of the nodes being switched. However, not all relays have sufficient clearances internally to switch 50 volts or 400 volts, so we need to be careful to pick an appropriate relay. And also, relays tend to have worse lifetime than solid-state switches. That is, in general, you can switch a mechanical switch fewer times than you can switch a transistor. FETs are a tempting option for those switches due to their longer lifetime. But the control gets tricky since the control voltage of a FET is relative to its source. Since every FET in the circuit has a different source voltage, the control voltage also is different for each FET. We need what's called a level shifting circuit for every switch to level shift from some microcontroller's digital signal to whatever voltage range each switch needs. Only the bottom switch, the one connected to the constant 0-volt ground, can be controlled directly by the microcontroller or other ground reference digital circuit. Let's summarize. Active balancing conserves energy, but requires more complex and thus expensive circuitry. In my experience, the value of the energy lost to passive balancing is quite small relative to the cost of active balancing hardware. This is the end of the video on active balancing in the cell balancing lecture. And this completes the lecture on cell balancing in my Battery Management Systems course. If you liked what you saw, please help this course get seen by sharing it on your favorite social media.